Welcome students. Welcome to the session 6. In this session, we are going to study frequency response, Nyquist plots. In the Nyquist plots, initially we will have to study the principle of argument. We will go through gain and phase margin, and later on we'll finish the session with some knowledge of Bode plots. In the previous session, we saw how to draw and analyze the stability using root locus technique. Now, from this session onwards, we'll be going into frequency domain analysis. Using frequency domain analysis, we'll be looking at different gains and different phase of different transfer functions. Let us look into the contents of this particular session. What will you learn in this particular session? We will start with general representation of any transfer function in frequency domain. We will be looking at magnitude response of a transfer function. We will also see how to represent a phase response. In the second topic, we will study what is a principle of argument, and we will go to Nyquist contour. Now, topic number 2 and 3 are closely interlinked to study the Nyquist stability criteria. Up till now, in Routh criteria and in root locus technique, we saw open loop stability. We saw how to determine the stability of open loop system or a closed loop system. So we had the knowledge of closed loop poles and closed loop zeros, and we could find out the closed loop stability, or we had the knowledge of open loop poles and open loop zeros, we could find the open loop stability. But in Nyquist stability criteria, from the knowledge of open loop zeros and open loop poles, we will be able to determine the closed loop stability. That means even if we just have the system parameters for the open loop system, we will be able to determine the stability for closed loop. After studying the Nyquist contour and the Nyquist stability, we will go towards looking at closed loop stability and polar plots. Polar plots are studied because polar plots are closely interlinked with Nyquist contours. We'll be looking at how to draw Nyquist contours, and to learn how to draw Nyquist contours, it is very much required to know how to draw polar plots. After we know how to draw the polar plots, we'll be comfortable in drawing Nyquist plots, and we will be comfortable with Nyquist stability criteria. We will go through gain and phase margin and also Bode plots. Gain and phase margins are some of the important topics in control systems on which different gate problems have appeared in last few examinations. We'll be looking at gain and phase margins conceptually right now, and we will solve the problems related to all these topics in problem sessions. Let us go forward and see the frequency response. We will start with the representation of frequency domain of any transfer function. We will see how to calculate a magnitude response and phase response of a transfer function. Let us see what is frequency response. So as you know, we have any system, any transfer function g of s. We can write s as sigma plus j omega. Now, this frequency omega is the range of frequencies. Okay. Now, omega being the range of frequencies, we could put lot many values into this omega and find out the value of g of s. As you know, s is a complex frequency represented as sigma plus j omega. We will be getting two parts of the response of g of s. One will be magnitude and other will be phase. So according to different values of omega, we will be getting different magnitude of g of s and also different phase of g of s. G of s will no more be g of s, it will be represented as g of j omega. Okay, so this is generally how you will represent any transfer function in s into j omega, just by replacing s by j omega. And to find out magnitude, you will just have to calculate magnitude of function g of j omega, and to calculate phase you will just have to calculate the combined angle of g of j omega. I'll just describe you now how to calculate magnitude and how to calculate the phase of a particular transfer function. Let me erase everything on this particular. Thank you. So just imagine, just take an example. Let us say g of s is equal to 1 plus 1 upon s plus 2. If I want magnitude response and phase response, what I'll do is I'll represent g of s as g of j omega, writing this as 1 upon j omega plus 2. Now I am interested in magnitude, so I will write g of j omega magnitude is equal to 1 upon magnitude of this particular complex function. As you know, for any complex function a plus ib, magnitude is given by root of a square plus b square, which is nothing but root of real part square plus imaginary part square. Similarly, we will do this here. So we will square omega and we will square the 2. So the magnitude will be given by 4 plus omega square. Okay. So this is how the magnitude of this function will be written. Now let us find out the phase of the function. Now angle of g of j omega will be given by angle of numerator minus angle of denominator, which can be given as tan inverse of 0 by 1, imaginary part by real part for numerator. Here imaginary part is 0, so we can write 0 here, and minus tan inverse of imaginary part in denominator, which is nothing but omega upon 2. So this is how you calculate magnitude and phase of a particular transfer function g of s. So first step is to convert s into j omega, and then we can find out the magnitude response as well as phase response. As you can see, phase response is represented by phi of j omega or angle of g of j omega. Okay, we will go forward and see the principle of argument now. Principle of argument is a particular theorem in complex algebra. Nyquist, who is a control systems scientist, used this particular complex algebra theorem, to determine the stability of a closed loop system. We will slowly explore the principle of argument, and we will go towards step by step the stability analysis given by Nyquist. We will go forward and first study what is principle of argument and how Nyquist applied this particular argument to get the stability analysis. Let us see the principle of argument. So let us say Q of S is a ratio polynomial be n of S upon d of S. Okay. Now, according to principle of argument, we are going to draw two graphs or the mapping system, in which one of the mapping will be of S plane, and this S plane will be mapped into QS plane. Alright. Now, we already know the roots of numerator, let us call them zeros or say Z, and roots of the denominator will be called poles, let us call it P. Now, if we have to plot these zeros and poles into the S plane, so you have a particular function Q of S, which is given as n of S by d of S, and you already have determined the zeros and poles of this particular transfer function. Then let us assume if you have a particular pole in here in the S plane. So according to principle of argument, if you take any point, random point S in this particular plane and calculate the angle, okay, and move this point now clockwise around the pole. Okay, so this is a pole, and you have moved a particular point S around this particular pole and measured the angle at every point. So this particular mapping will be done in Q of S plane, which is nothing but real part of Q of S and imaginary part of Q of S. So mapping of such a contour around a particular pole will be done in clockwise direction encirclement of origin in QS plane. Okay, so this is clockwise encirclement of the origin O, and here is a pole which is encircled or which is enclosed by a contour clockwise. So there are three important terms here. Sorry, this is not a pole. This is a zero. So which is shown by a hollow dot. This is a zero that I am talking about. Zero of n of S. Okay. So this is a zero which is enclosed clockwise in the S plane. Then it will be transformed or mapped in the QS plane as the clockwise encirclement of origin. Alright. So remember this. For a zero, the enclosed clockwise enclosure of a particular S-plane contour maps as the clockwise encirclement of origin, because Q of S is equal to 0. So origin is Q of S is equal to 0. Now we will do this same analysis for pole, that is the root of denominator or the root of d of s. So let us see what changes when we enclose a pole. Now you have q of s is equal to n of s by d of s, where root of d of s is nothing but a pole, okay, which is shown as a cross. Now let us draw an S-plane where you have, let us say you have a pole here. You can draw pole anywhere, and if you enclose this particular pole clockwise, okay, so if you enclose a particular pole in S-plane clockwise, all these points are nothing but the locus of any random point S. So this is S-plane sigma plus j omega, and this will be mapped as anti-clockwise encirclement around origin for QoS plane. Okay, so this is what the principle of argument says. So that we saw, if there is a pole lying in S-plane and if it is enclosed clockwise, so you get anti-clockwise encirclement of origin. Okay, so for a pole you get anti-clockwise encirclement, and for a zero you get clockwise encirclement around origin of Q of S. Now we will try to translate this particular discussion into mathematical equation. Let us call Z, so those zeros which are enclosed by S-plane contours. Okay, so Z is the number of zeros of Q of S, or say N of S, which are enclosed by the S-plane contour. This S-plane contour is the user defined contour. It can be anything. It can be here, it can be like this, or anywhere. So let us say Z be the number of zeros which are enclosed by S-plane contour, and P be the number of poles which are enclosed by S-plane contour. Okay, this is also the same thing for Z. And let us call, I will just write down, so N be the number of encirclements of origin clockwise in Q of S plane. Okay, so that you know. Now if for a particular zero, if the S-plane contour goes clockwise, then you get one encirclement clockwise for QS plane around origin. For the pole, if there is clockwise enclosure in S-plane, you get anti-clockwise rotation around origin. So you get the equation as Z minus P is equal to N, right? Z are nothing but the enclosures clockwise, P have the enclosures clockwise, which gets subtracted because they have negative effects on the encirclements, and we call clockwise encirclements to be positives. Hence, according to principle of argument, you have this equation. Z minus P is equal to N, where Z, P and N are as defined. Now, the catch here, or the important point to remember, is we can transfer this particular principle of argument to the stability analysis in closed loop systems. So if you have Q of S is equal to 1 plus G of S H of S, yes, we can write this as like that. For Q of S, origin was 0, but for a system like this, if you equate to 0, my origin will be minus 1 plus J0. Okay. So just remember, for G of S H of S, the origin is nothing but point minus 1 plus J0. So this is what we are looking at. As we already discussed that the S-plane contour maps into QS plane contour as a closed curve. Let us see some of the conclusions from principle of argument. As I already described, because of principle of argument, you have this simple equation Z minus P is equal to N, where Z is the number of zeros of 1 plus G of S H of S, which we just transferred as Q of S. So we are replacing Q of S by 1 plus G of S H of S. So Z are the number of zeros of Q of S enclosed by S-plane contour, which is this S-plane contour is user defined. Okay, so this is user defined. This can be defined as anything, any contour. P is number of poles of G of S H of S enclosed by S-plane contour, and N are number of clockwise, remember clockwise encirclements of the critical point 1 plus J0. Critical point is nothing but origin. Okay. So, N are number of clockwise encirclements around origin, which is nothing but 1 plus J0. Not 1 plus, it should be minus 1 plus J0. Okay. By G of S H of S plane contour. Let us see what Nyquist did with the principle of argument. As I already mentioned, the S-plane contour is user defined. Okay. So Nyquist actually designed such a contour so that we could find closed loop stability of Q of S is equal to 1 plus G of S H of S. Okay. So Nyquist actually chose such S-plane contour so that we will be able to find out the stability for 1 plus G of S H of S. As we already know, Z minus P is equal to N according to the principle of argument. Now, Nyquist used the logic that we already know for S-plane sigma plus J omega, if the poles of a function lie in right half of S-plane, if poles are lying on the right half of S-plane, the system will be unstable, right? So that means if there is a system which detects if there is any pole on the right hand side of S-plane, then I will be able to comment on the stability of the system. So this is what Nyquist did. Let us see the Nyquist contour, which was user defined S-plane contour. Okay. Now scientist Nyquist decided that this user defined S-plane contour can be all the right hand side of S-plane. So he selected a contour with infinite radius but a semicircular region on the right hand side of S-plane. So this is the Nyquist contour, which is S-plane contour. Okay, so this is how we are going to look at the Nyquist contour. Now, if there is any pole or a zero on the right hand side of S plane, we will have some positive values of Z and P, and we will be getting N. Now, the catch here is we know what N is. Yes, we can find out the encirclements. That means I am trying to make a point to tell you all that we can build or draw the 1 plus g of s h of s contour. Okay, so the contour that you see on the right hand side, which is nothing but the QS plane contour. Okay, this can be drawn by the knowledge of g of s h of s, and as you will be able to draw this particular contour, you will be able to get to know the encirclements of this particular contour around the origin minus 1 plus j naught. Okay, now you know N, you have a Nyquist contour to detect if any pole lies on the right hand side of S plane. Okay, so now one more thing, these Z and P are open loop zeros and poles, open loop. Okay, but we are interested in closed loop stability. As you can see, often we have system as 1 plus g of s h of s. Okay, so this is the closed loop system always. Z and P are the zeros and poles of this particular equation. Now, open loop zeros, which are zeros of g of s h of s, are nothing but closed loop poles. Okay, so if these closed loop poles lie on the left hand side, my system will be stable. That means if my open loop zeros lie on the left hand side, my system will be stable. Translating this again into some logic, if my open loop poles do not lie on the right hand side of S plane, my system will be stable. If my open loop zeros, that means Z, are not lying on the right hand side of S plane, that means I'll be getting no enclosure for my open loop zeros for Nyquist contour, which is on the right hand side of S plane. That means for my system to be stable, the value of Z should be 0. Right? That is exactly what Nyquist told. So for closed loop stability, let us see. Nyquist said for closed loop stability, open loop zeros, that means Z should be 0. And in equation, if you put Z is equal to 0, you get N is equal to minus P. Now I know what is the value of N, as I can draw a 1 plus g of s h of s plane. Okay, or we can call this a Nyquist plot. So one is a Nyquist contour and another is Nyquist plot. So you can determine the value of N by having to draw this particular Nyquist plot, and you just need to check if n is equal to minus p. Okay, so these p are nothing but open loop poles. So if n is equal to minus p, you will know that the system is stable. So this is how you can determine the closed loop stability by just drawing the Nyquist contour and determining if how many encirclements are there around -1 plus j naught origin, and then looking at the number of poles or the enclosures of poles by Nyquist contour. As I already described, z are number of zeros of 1 plus g of s h of s enclosed by Nyquist contour, and p are poles. Let us look forward and see what are further criteria for closed loop stability. Most of the times p will be also 0. So there will be no open loop poles also which will be lying on the right hand side of S plane. Most of the times, but not every time. So if n is equal to minus p, and if most of the times p is also is equal to 0, what should be my criteria for stability? Yes, n should be is equal to 0. Okay, for stability, closed loop stability. Okay, for closed loop stability, if n is equal to 0, my stability criteria suffices. For that, p should also be equal to 0. Now, how to draw a Nyquist contour? This is the main question. If you are able to draw the Nyquist contour, you will be able to calculate the value of n. Okay. Nyquist contours are nothing but mirror image of polar plot across real axis. So if you can draw a polar plot of a system, say if you have a system 1 plus g of s h of s, or just g of s h of s, and if you are able to draw g of s h of s polar plot, okay, you will be able, if the polar plot is like this, coming from here to here, and if there is this -1 point, Nyquist plot is nothing but mirror image of polar plot across real axis. So this is a real axis. Across this axis, I have to draw mirror image. Okay. Sorry for my drawing, but this is how something will be the mirror image of the polar plot, and this will be my Nyquist plot, and we will check if this particular enclosure encloses -1 and for how many times clockwise. So this particular contour encloses the -1 origin for 1 clockwise. That means n is equal to 1 in this particular example case. Okay. So as n is equal to 1, I'll have to check if my p is equal to -1. That means p should be lying on the left hand side of SP. So p will not be -1. P cannot be -1. P might be 0 or positive. P just cannot be negative. Okay. So this is how I can say system will be unstable if n is equal to 1. Okay. Let us now check how to draw polar plots, and after that we will see how to draw Nyquist plots. Let us go to the next slide and see some of the typical polar plots that we have got. Initially, we have a polar plot for a transfer function 1 upon 1 plus j omega t1. This is a typical first order transfer function. We will calculate the polar plot. Now, what is a polar plot? Polar plot is nothing but the locus of tips of the phasors of this particular transfer function. Okay. So if you put different values of omega, and calculate angle and magnitude at the same time. As you change omega from 0 to infinity, you will get a particular locus of tips of phasors. So this will be a first phasor, this will be second phasor. This is how my tips of phasors will vary, and as the value of omega goes to infinity, my magnitude will tend to 0, and this is how I'll get the smallest phasor at around 0. As you can also see, the phase j omega here is nothing but minus tan inverse of omega by 1. So as you put omega towards infinity, the angle will be negative, and that is essentially why angle goes from 0 to infinity towards for minus tan inverse of infinity, which is the limiting value of omega, you get minus 90 degrees. So, and for omega equal to infinity, you get magnitude of this particular g of j omega is equal to 0. Okay. For omega equal to infinity, angle is at minus 90 and value or the magnitude is 0. Similarly, for omega equal to 0, you have length of is equal to 1 and the angle is equal to 0. So this is the polar plot for the transfer function 1 upon 1 plus j omega t. If you know the direction is going from omega equal to 0 to omega equal to infinity. So for this polar plot, I have system something like this. Okay. And the length is equal to 1. Now to draw a Nyquist plot, I have to take a mirror image, which will be like this. But the arrow direction should be opposite while drawing the Nyquist plot. This is the important point to remember, that here the arrow is in this direction, but now in this particular Nyquist plot, arrow will be in this direction. Okay, so this is how the arrow will go in Nyquist plot. But for this function, minus 1 point is here, and this particular Nyquist plot is not even crossing 0. So in this particular system, n is equal to 0, and hence this system that we are seeing is stable. Okay, for n equal to 0, this system is stable. As you can see, for t1 greater than 0, 1 plus j omega t1 will have the open loop pole to be on left hand side of sk, and that's why we have t equal to 0, and that's why the system is stable. As n is equal to 0 suffices. Let us erase this particular function. Let us look at this second function on the bottom, wherein the transfer function is 1 upon 1 plus j omega t1 plus 1 upon j omega t2. Similarly, if we put the values of omega into this function, you get a polar plot like this with direction in this direction. Also, polar plot cuts the imaginary axis right here. Okay, so this value can be given by 1 upon t1 and t2 under the root. So if you want to find out this particular value, you can find this out by 1 upon root t1 t2. Also, this particular magnitude is given by root of t1 t2 divided by t1 plus t2. Drawing the Nyquist plot, you will have such a diagram, a heart shaped, going towards origin, and again taking the mirror image, but the direction will be opposite. So this is how the counter will look like. This is also a counter which does not include -1 point, and that's why these two poles lying on the left hand side of his plane, here also n is equal to 0 and p is equal to 0, and hence the system can be called as. Okay, let us look at different figures for this particular function. If you have such a contour, if you recreate the Nyquist contour, you get such a figure, and for a different arrow on the opposite side, still here -1 plus j0 point is not encircled. Again, n is equal to 0. For poles lying completely on left hand side of S plane, this is the pole on origin which is not covered by Nyquist plot, so n is equal to 0 again. We have a function number 4. Here, this particular function may or may not cover the encirclement or cover the -1 point j0 point. If we try to draw the mirror image of this particular function, looks like this. If we want to draw a mirror image, so this is the mirror image of this particular Nyquist plot. This goes in this direction initially, so direction will be opposite. This is how it is going. So it will go like this and go like this. So if my -1 point j0 point is here, n will be 0, but if my -1 plus j0 point is inside the circle, it will have one anti-clockwise and one more anti-clockwise encirclement. That means my n will be -2, and for my system to be stable, I must have two poles lying on the right hand side of S plane. These poles are nothing but open loop poles. So I do have two poles, and hence T1 and T2 should be less than 0. This is how I will be getting my system to be stable. Okay, let us go forward and see the third graph. Here again you have encirclement. You might or might not have encirclement. Again, drawing this particular Nyquist plot, the original direction will be in this direction. So in Nyquist plot, direction should be opposite. Let us first make the direction opposite and then draw the mirror image Nyquist plot, wherein then we will solidify it now. So let us draw the arrows now. So this is coming from this side and going with this arrow. So if my -1 plus j0 point is inside this contours, so I will again get 1 and 2 anti-clockwise encirclement, and hence n will be -2. So this is how I can calculate the encirclements, and this is how I can draw the Nyquist plots according to the knowledge of polar plots. As I mentioned, for polar plots you have to calculate angle and the phase. Put omega equal to 0 initially and put omega equal to infinity for limiting cases. Calculate tan inverse of numerator minus tan inverse of denominator, and using this calculate phase for these limiting values and try to join the values. Okay, this is how you can find out the value of n. Having completed the Nyquist plots and Nyquist stability, and I hope all of you must have understood the Nyquist stability. We can safely now go forward and look at gain and phase margin and Bode plots. These are simple concepts, not very difficult concepts to understand, but there are some critical and complex problems that appear in the exams. We will be solving such problems in problem sessions. For now, we might look at important concepts related to gain and phase margin, in which we will be looking at gain crossover frequency, phase crossover frequency, and Bode plots. Let us see what is a gain margin and phase margin. Okay, to initially look at what gain margin and phase margin is, we first should look at what is a phase crossover frequency and what is a gain crossover frequency. Let us look at what is gain crossover frequency first. Okay, so it is the gain crossover frequency where g of j omega g plus h of j omega g is equal to 1. So when you have a transfer function g of s and h of s, when you transfer this transfer function as g of j omega into h of j omega, and if you calculate the magnitude, and if you get magnitude, if you equate this magnitude to be 1 and find out the value of omega, you will get omega is equal to omega g, which is nothing but the gain crossover frequency. Okay. Also, what is phase crossover frequency? This is the magnitude. This is the magnitude calculation. Similarly, you can calculate the angle of g of j omega and h of j omega. If you calculate the angle of g of j omega and h of j omega, let us say tan inverse of numerator minus tan inverse of denominator, and equate it to get minus 180 degree and find out the value of omega. This omega should be equal to omega p or omega phi. Okay, so this is known as phase crossover frequency, and this is known as gain crossover frequency. Okay, so this is how you calculate gain crossover frequency and phase crossover frequency. Let us see what is gain margin and phase margin. Gain margin is essentially the margin available for gain, so that we can still increase the gain to get equal to 1. So if you have the current gain of 0.25 and I know my gain limit is 1, so I wouldn't like my gain to cross 1, because in negative feedback I know my gain is less than 1, and if my gain increases than 1, my system might turn to be unstable. So I can still increase my current gain, which is currently 0.25, by the multiplier 4. So my gain margin will be 4. Okay, so this is how I can calculate my gain margin. Essentially, this formula can be given by gain margin is equal to inverse of g of j omega phi upon h of j omega phi. Look at this term closely, that is omega phi is there. So initially, to calculate the gain margin, you will have to first calculate the phase crossover frequency, omega phi. So once you calculate phase crossover frequency, you will put that value of omega into g of j omega into h of j omega, and then you will calculate the gain margin. Okay, so remember, first you'll have to calculate phase crossover frequency. Okay, similarly you can calculate phase margin, but for phase margin initially you will have to calculate gain crossover frequency. So for phase margin calculation, first step should be to calculate the gain crossover frequency. Okay, so This is how you will calculate omega g and put that into phase margin equation. The phase margin is given by 180 degrees plus angle g of j omega g, h of j omega g. This is the phase with gain crossover frequency. Okay. I hope you have understood how to calculate gain and phase margin. Let us see graphically in the Nyquist plots how we can see gain and phase margin. Let us say this is the unity circle for unity gain. Okay. I would like my system in this particular region inside the unity gain. Okay. So I have all the frequencies, and now the frequencies from this point to this point, I have my gain less than 1. Okay. So as you can see, I have a gain crossover frequency here. That means gain increases than 1. So after this point, I have frequencies for which gain is more than 1. So this is the critical frequency for me. After this particular frequency, I will have all those frequencies for which my gain will be less than 1. So this is my gain crossover frequency, where this particular Nyquist plot, this is nothing but a Nyquist plot. It extends like this. If I am to draw the Nyquist plot, this is essentially a polar plot, but I'm extending this to be as a Nyquist plot. So this is a Nyquist plot. So this Nyquist plot, when crosses the unity circle, I get my gain crossover frequency. Okay. Similarly, you have phase crossover frequency here. If these frequencies values cross the minus 180 degree phase, I get my phase crossover frequency. Okay. I can calculate gain margin and phase margin as, I can calculate this small a by the knowledge of phase crossover frequency. So I know a. Now I just want to multiply this a with x. So a multiplied by some value x is equal to 1. So this is actually my gain margin. That is why gain margin is given by x is equal to 1 upon a. And this a is nothing but the magnitude of transfer function. It is nothing but g of j omega, but this omega is nothing but phase crossover frequency, and that is why this is omega 5. Okay, h of j omega. So this is how I calculate my gain margin. Understood? Now let us see what is phase margin. Okay, I'll erase all this and let us see what is a phase margin. Now my gain, when a particular frequency forces my gain to cross 1, this is my limiting value now. My system is already going unstable. So after these values, I have my stability, because you know here the value of omega is less, and in this direction my value of omega is more. But now as I cross my gain crossover frequency, I do have this particular angle. This is my phase at gain crossover frequency, and I still have this much amount of phase so that I can reach minus 180 degrees. So I do have this much margin to cross minus 180 mark. Okay, so this is the direction of frequencies. So Fm is the phase margin. You just have to calculate this angle for a phase margin. Okay, for this particular phasor, you know F. This particular F. Okay. Now what you have to do is you just have to subtract minus 180 degrees out of F to get phase margin. Okay. Alright. This is how you calculate phase margin for a system. Let us go forward and see how to draw Bode plots. Bode plot is nothing but the magnitude plot versus frequency. So if you have magnitude g of j omega, assuming h of j omega to be unity, if for certain frequencies magnitude increases so much that you will have to use logarithmic scale, and this is why you can use Bode plots, wherein on the x-axis you have omega and on the y-axis you have the logarithmic frequencies. So you have 20 log g of j omega, which is calculated as dB. So if you have g of j omega to be equal to k, let us say k is equal to 100, we will find out what is the value of 20 log magnitude g of j omega, which is given in decibels. So for k equal to 100, we will have 20 log k is equal to 40 dB. So for k is equal to 100, I will have 40 dB mark for my transfer function. And for all the frequencies, my magnitude is same. So this is how for g of s is equal to 100, my Bode plot will look like. There are a lot of problems in GATE exam where you have to determine the transfer function by looking at the Bode plot, or you have to calculate, or you have to just calculate some terms on the Bode plot using the transfer function. Let us see another simple example wherein we can see that if g of j omega is equal to k upon s, so that means 20 log g of j omega is nothing but 20 log k minus 20 log omega. So for omega, changing from omega 2 to omega 1, which is 10 times, we will have a graph as, so this is my 20 log g of j omega. So this is my 20 log k, and I do have the pole on origin. Okay, so from origin itself, from this particular value 20 log k, this is my magnitude value. Okay, this is my magnitude. So this is the equation of line, straight line with slope minus 20 log omega. Okay, and for decade change in frequency, I will have minus 20 dB per decade. Okay, so this is my 20 log k, and this is my Bode plot, wherein if this is my omega 1, this is my omega 2, wherein omega 2 is 10 times omega 1, and this is minus 20 dB per decade. So this is how I can plot different Bode plots, and we will be looking at different examples of Bode plot, different combination of Bode plots in problem sessions. For now, let us look at the session summary. We saw that frequency domain analysis provides special insights into stability of the system. Also, we saw that for Nyquist contour, which covers whole right half of S-plane. Nyquist stability is given by P is equal to minus N, where Z is equal to 0. N is the clockwise encirclement of G of S H of S plane around critical point minus 1 plus J naught. Also, Nyquist plots or G of S H of S S plane contours are mirror images of polar plots with respect to real axis. We saw that gain crossover occurs at gain is equal to 1 and phase crossover occurs at phase differences of minus 180 degrees. Bode plot is a magnitude versus frequency plot. The more problematic insights into Bode plot will be covered in problem sessions. Thank you.